All right, so we're going to move into section 2.3, which is graphing polynomial functions. Before we actually get into the graphing, we're going to talk about behaviors of the graph, which is important because if you know the behavior of the graph based on the degree of the function and the leading coefficient, you can then have a better chance of graphing it accurately with the least amount of work possible. So we're just going to run through some examples of what these graphs could look like based on just the degree of the function, right? So that's the largest exponent. So first degree, that's a linear function. And you know, it looks like this line right here, right? This line it has a positive slope, but the important part here we want to focus on is the end behavior of the curve, which is either what's happening to the y values as the graph moves left and what's happening to the y values as the graph moves right. We're going to first focus on as x increases moving right, what's happening to the y values. These y values appear to be increasing based on this graph, which would dictate that this is a first degree polynomial with a positive leading coefficient, okay? There are 0 turns in this graph, it's just a line, right? And we'll start connecting pieces as we move through. Now, second degree polynomials, these are quadratic functions, you know what they look like. Again, focus on the right side of the curve. The right side of the curve is increasing as x moves to the right, which means that the leading coefficient, which is what we call a in a quadratic, must be positive. And if you count the number of turns, there's only 1 turn in this curve, whereas in the linear function, there's 0 turns, all right? So we're trying to connect patterns. Third degree, in this particular case, this graph has 2 turns in it, right? And when I'm talking about turns, I'm talking about, you know, this is a turn right here, that's 1 turn, this is another turn too. This graph also has 3 x-intercepts, as well as the quadratic here had 2, and the linear had 1. So this is third degree polynomial. Now the end behavior of this graph is going down as we increase, which means that the leading coefficient, the a value, must be negative, okay? So first we're just going to look at a few things between these 3, first degree, second degree, third degree. So first and third degree polynomials here are connected because they're odd, okay? That means the largest exponent is an odd number. Whenever that happens, we're always going to have a graph that travels in opposite directions for the y values, right? So in this case, as x moves this way, this graph is going down, and as x moves this way, this graph is going up. So when I say opposite end behaviors, right, that's what we're talking about. The second degree polynomial, right, this has a curve in it, it's like a U, so in both cases, as x goes to the left here, this graph goes up. As x goes to the right here, this graph goes up. All right, so that's your second degree polynomial. So in the even degree polynomials, the ends of the curve, right, these 2 ends here are going to be traveling in the exact same direction. And because this graph particularly is increasing, right, then that means a is a positive. Now, third degree polynomial, again, if you look at the end behavior, as x goes to the left, this graph is going up. As x goes to the right, this side of the graph is going down. All odd degree polynomials will have this opposite end behavior, just like the line did, right? One side is going up, one side's going down, one side's going up, one side's going down. But in this particular case here, because the right side of the graph, right, as x increases here, the right side of the graph is going down, right? Which means the a value here would have to be negative for that to occur. And then these patterns are going to be pretty consistent as we move to the 4th, 5th, and 6th degree, right? So 4th degree is an even polynomial. That means that both ends of the curve should be going in the exact same direction as they are here. The right side of the curve, right, as x increases this direction, the right side of the curve is going in the positive direction here. That means the a value, the leading coefficient, must be positive. It has 3 turns in it if you count, right? So that's exactly where the graph is turning, right? So 1, 2, 3, and it also has 1, 2, 3 x-intercepts, right? So remember the number of roots or zeros a polynomial has must be identical to the degree. So this is a 4th degree polynomial, and I think I just miscounted there. 1, 2, 3, 4. There's your 4 roots. 3 here is indicating the number of terms it has, so this one has four real roots. Okay, 5th degree. It's an odd polynomial, which means that the end behavior of the curve should be going in opposite directions here. As x decreases on the left, it's going down. As x increases on the right, it's going up. Also, on the right side of the graph, as x increases, it's going in the positive direction, which means the leading coefficient must be a positive number. What else do we have? Counting number of turns. So we have 1 turn here, 2, 3, 4. Okay, so there's 4 turns in this graph. Okay, so now we're going to start making connections, right? So we've looked at the number of turns so far. For a line, there's 0 terms, the degree is 1. For a quadratic, there's 1 term, the degree is 2. For a cubic, there's 2 terms, the degree is 3. So at this point, you should be noticing a pattern that the number of turns the graph will have is 1 less than the actual degree of the polynomial. So in this case, we have 1, 2, 3 turns, but this is the 4th degree. So 5th degree, we're counting 4 turns, right? Again, that's 1 less. So on the 6th degree, over here, we should have 5 turns, and if we count them, we do. There's 2 turns right there. All right, so that's 1, 2, 3, 4, 5. 5 turns, right? 1 less than the degree. Also, the end behavior is going in the exact same direction. That is consistent with even degrees. All even degrees go in the opposite direction, or same direction, excuse me. And then we're also noticing that as x increases here, the right side of the graph is going down, which means the leading coefficient a must be negative. And now we're counting roots, x-intercepts, right? I can clearly see 2 right here. 1, 2 real roots there, right? But this is a degree 6, which means we need to find 4 extra roots. In this particular case, those roots or zeros, they're not real numbers, so we cannot point to them on the graph. So we can see 2 of them now, but if there's a total of 6, that means 4 of them must be complex. The number of complex roots or zeros plus the number of real roots or zeros must always equal the degree of the polynomial 6 in this case.